I was sitting in a study hall the other day preparing for a high school trig test, and I came across these two triangles. Two right triangles, the side lengths of which are all integers. An integer is a number that is not a decimal or a fraction. The rule with right triangles is that the square of this side and the square of this side added together have to equal the square of this side. We usually write that as a squared plus b squared equals c squared. I'm sure you've all seen that equation many times before. But I'm sure you've also seen a 3, 4, 5 and a 5, 12, 13 triangle many times before. These triangles are both very famous. But what if I told you that another right triangle with integer sides looked like this? 8, 15, and 17? It doesn't look very good, but it does work. You can plug it into your calculator right now. 64 and 225, take the square root, and you get 17. My name is Sam Griffith, and I hope you stick around with me today as I show you my method for creating a right triangle with 3 integer sides, one side of which being any integer you want. Then I'm going to show you my proof that it works no matter which integer you choose. I may be a bit biased, but I personally think that this is one of the coolest math proofs I've ever seen, probably because I created it. But regardless, I hope you keep watching, and I hope you enjoy it as much as I do. The first step in coming up with this method is realizing that perfect squares increase by 2 more every single time. And that's not a very good way of describing it, but I'll write it down and show you. 1 squared is 1, 2 squared is 2, 4 minus 1 is 3, 3 squared is 9, minus 4, 5, and you'll find that as you go down the list, you go up by 1 odd number every time, also known as adding 2. You'll get 3, 5, 7, 9, 11, 13, 15. And this pattern continues on forever. It doesn't stop. But what's cool about this is 9 itself is a perfect square, right? 9 is 3 squared. We can take the Pythagorean theorem, a squared plus b squared equals c squared, and subtract b from both sides to get c squared minus b squared equals a squared. So what does that give us? That shows us that 5 squared minus 3 squared is 4 squared, right? 25 minus 9 is 16. 5 squared minus 3 squared is 4 squared. C squared minus b squared is a squared. Remember our triangle from before? 3, 4, 5. But that doesn't mean anything, right? That's just luck. Now you might still be wondering what that has to do with anything. But it'll make more sense when you realize that there's an infinite number of these perfect squares amongst the differences between the squares. So if we have, I don't have a good eraser, I just have my hand. If we have, what's our next one? 5, 12, 13? If we have the difference of 12 squared and 13 squared, 144 and 169, we'll notice that the difference between these two numbers is 25. 25 looks familiar, right? It's 5 squared. That's where 5, 12, 13 comes from. So now we found 3 squared and we found 5 squared among the differences between perfect squares. But what you'll notice is that these numbers are all odd. 3 squared, 5 squared. So the next number that we have to look for in this sequence is 7 squared, 49. But we got to figure out how in the heck we find 49 among these numbers, because we don't want to write out every single one of these. So what you can notice is 5 corresponds to 9, we'll say. 13 corresponds to 25. How do you go from 5 to 9? Well, for starters, you can multiply by 2 and subtract 1 to get 9. 13, you can multiply by 2 and get 26 and subtract 1 and get 25. So, if we want to find 49, we have to reverse that process. We have to add 1 and then divide by 2 to get 25. 25 squared, 24 squared. The difference between these squares, I don't even have to calculate it, I just can know that the difference between these squares is 49. That means that there is a triangle that is 7, the square root of 49. Remember, this is b squared, 24, which is a squared. We don't have to write the square. We just take a, and 25. You'll find that this can be done for any odd number. So you want to find the triangle for 9. What we can do is we can use the same process. 81 plus 1 is 82. Divide by 2. 41 squared. 40 squared. The difference between these is 81. Triangle 9. 40. 41. The next step is to write that process down in a formal way so that we don't have to think through it quite so sporadically every time. If we call this side n, we want to know what this side is and what this side is in terms of n. So what we have to do is we have to write out the process that I was just doing algebraically. And if you think about it, what I was doing is I was taking n and I was finding it in this row, right? I was finding the square of it in that row. We'll say n is 3 for now. What I was doing is I was finding 3 squared, in other words 9, in this row. So we can write n squared. Then I was taking this number and I was adding 1. We'll do it up here. N squared. And I was adding 1. And then I was dividing by 2. And what that gets you is this number down here, right? The upper end. So once you get this number, what you're finding is this 5. You're saying that this is n squared, 9, plus 1 over 2, 5. But what you'll notice is because it's the number that you're finding on this side is always the difference between consecutive perfect squares, all you have to do is take this number and subtract 1 to get the number before it. Because the perfect squares are consecutive, that always works. So n squared plus 1 over 2 minus 1. But minus 1 can also be written as minus 2 over 2, right? So it's n squared plus 1 over 2 minus 1, but n squared plus 1 over 2 minus 2 over 2, because 2 and 2 simplify to 1. That means that we can actually rewrite it as n squared plus 1 minus 2 over 2. And if we combine like terms, we get a much easier to read fraction that looks like this. Excuse my erasing method. N squared minus 1 over 2. And what you'll find is that if you plug in any odd number for n to this triangle, you will get 3 integers every single time. But I can already hear you asking, what happens if I don't like odd numbers? And if I was a lesser man, I would tell you to grow up and learn that odd numbers are great, because they are great. But I'm not a lesser man, so I'll show you how to do the same thing with even numbers. Just like there's an infinite number of perfect squares among the difference between perfect squares, there's also an infinite number of sums of the differences between perfect squares that equal perfect squares. Right? 16 is 4 squared. But that means that the difference between 5 squared and 3 squared is 4 squared, right? In other words, 25 minus 16 plus 25 minus 16 is 9, plus 16 minus 9 is 7, is the same as 5 squared minus 3 squared. But how does that help us? Well, let's start by writing 4 as our n. We know that 4 squared is 16, which is also 7 plus 9. But how do we get from 4 to 5 squared and to 3 squared? Well, we can start with 4 squared to 16. And what you'll notice is that if we divide by 2, like we did last time, what you'll get is always the average between these two, right? You'll get 8. Because if you add two numbers and then you divide by 2, you're always going to get the average. So no matter what, the average of two consecutive odd numbers is going to be the even number in between them. So if it's 7 and 9, it's going to be 8. If it's 5 and 7, it's going to be 6. If it's 3 and 5, it's going to be 4, etc. So we take the average between 7 and 9, which is 8. And then how do we get from 8 to 5 and to 3? Well, you can subtract 3 or you can subtract 5, but the number that you've got to subtract is going to change based on how far down the list you are. So what you can do instead is you can divide by 2 again. So now we're dividing by 4 in total. And then you can minus 1 to get to the consecutive number before it, and you can add 1 to get to the consecutive number after it, because the different, or the sum that we're looking for is always going to be the difference of 3 consecutive odd numbers combined. So if you subtract 1, you're going to the one before. If you add 1, you're going to the one after. It's always going to be like that, no matter what number you're on. So n squared over 4 for the base side is going to be minus 1 to get the lesser number, and n squared over 4 plus 1 get the higher number. So now we have one triangle for odd numbers and we have one triangle for even numbers. And the only thing left to do is to prove that they always work no matter what. There's this thing in math called the strong law of small numbers, and it's that with smaller numbers, things like this tend to be easier, or they tend to seem like they work, and then when you get bigger and bigger numbers, those things stop working. But I can prove to you that in this case, it works no matter how big the number is. Let's start with the odd one. An odd number, by definition, is 2n plus 1. Right? It's a different n than this. Maybe I'll use a different variable because I don't want to get anything mixed up. I'll use x. 2x plus 1. Where x is any integer. Or x is an integer. Yeah. So an odd number by definition is 2x plus 1. First, what you have to understand is that any odd number times itself is going to be an odd number. Right? And it makes sense if you think about it. If you take an odd number of things, just imagine 3 dots, right? And you're saying an odd number is one that ends up with, if you pair as many dots as you can, there's one left out. If you take an odd number times an even number, what you'll find is that you get pairings with every single one. But if you take an odd number times an odd number, say 3 times 3 in this case, you get pairings and one left out. 2n plus 1. So, if n is odd, n squared is odd. If n is even, n squared is also even. But that means that if you have an odd number and you subtract 1, canceling this plus 1 out, and then you divide by 2, that cancels the 2 out, you're always left with an integer. You're always left with an integer. Same thing with 1. Because if you add 1 to 2x plus 1, what you get is 2x plus 2. And then the important thing is that 2x plus 2 is also an even number, because 2 is an even number. And an even number plus an even number is an even number. So n squared plus 1 over 2 is always going to be an integer because it's always going to be an even number over 2. Same thing with n squared minus 1 over 2. Always an integer because n squared minus 1 is always an even number. And an even number divided by 2 is always going to be an integer. Now let's prove that the right triangle for even numbers always works. I think this is personally my favorite part of this whole proof. We know that n squared, if n is even, n squared is also always going to be even. But what you might not first realize is that n squared will always be a multiple of 4. And it comes from the same thing, 2x plus 1, or no, not plus 1, sorry. 2x is an even number, right? Every even number is divisible by 2. That means that if you multiply 2x by 2x, in other words, you're squaring it, you get 4x squared. See? The 4. So then if you divide by 4, cancels out, subtract 1, it's going to be an integer. If x is an integer, x squared is an integer, and any integer minus 1 is also an integer, because 1 is an integer. I don't think the word integer sounds like it should exist anymore. I've said it so many times in a row. So every single value for n, if it's even, once you square it, it's going to be divisible by 4. And think about it. It's true. 2 squared is 4. 4 squared is 16. 8 squared is 64. I don't know past that. 12 squared is 144. Those are all divisible by 4. And that's not strong law of small numbers either. That keeps going on forever because 2x times 2x is 4x squared, and you can cancel out the 4. So now the final step is to prove that n squared minus 1 over 2 squared plus n squared will always be n squared plus 1 over 2 squared. And this comes from the Pythagorean theorem. We're just substituting the legs in. We're substituting a for our one leg, b for our other leg, and the hypotenuse for the hypotenuse of our new triangle. And we can do that, and we can prove that if we can find a way to manipulate this side into becoming this side, in other words, establishing the identity, we're proving that this triangle will always work as long as the Pythagorean theorem holds true, and it has shown to since ancient Greece. So I think it's a pretty strong case to make. So we can start off by distributing the square to the top and bottom of the fraction. N squared minus 1 squared over 2 squared, 4, plus, if we imagine n as a fraction n squared over 1, we can multiply the top and bottom by the same number, and we can get 4n over 4. Now we can add these two together to get 4n squared plus n squared minus 1 squared all over 4. If we work this out, n squared and negative 1, n squared and negative 1, and 4, negative n squared, and 1, we end up getting 4n squared plus n to the 4th minus 2n squared plus 1 all over 4. Combine like terms. We have n squared here, 4 minus 2 is positive 2, n to the 4 plus 2n squared plus 1 all over 4. We can turn this into, I'm running out of space, but we can turn this into n squared plus 1 squared by factoring that, and it's just the reverse of this, over 2 squared. Since we have a square on the top and bottom of the fraction, we can pull it out, and just write what we had originally, n squared plus 1 over 2. And look at that. N squared plus 1 over 2 squared, n squared plus 1 over 2 squared. We've established this identity. That triangle will always hold true no matter what. The next step is to, in an extremely similar fashion, establish this identity. Once again, we're just substituting a for one side, b for n, and c in the hypotenuse for this hypotenuse. We can do this exact same thing that we just did. First, actually, we're going to turn this 1 into 4 over 4 so that we can have a common denominator. N squared minus 4 all over 4. And then we square the top and bottom. N squared minus 4 squared over 4 squared, 16. We got to turn n squared into 16 n squared over 16. That way we can add it to this fraction. And what you'll end up getting, we should do this quick, but it will be n4, negative 4n squared, negative 4n squared, and 16. Once all said and done, you'll end up getting 16n squared plus n to the 4th minus 8n squared plus 16 all over 16. Next we combine like terms just like before. 16n squared minus 8n squared is negative 8n squared. You get n4 minus n4 plus 8n squared plus 16 all over 16. Once you factor that out again, you end up getting n squared plus 4 over 4, like that. My camera battery died, so it's been a few hours, but I'll try to pick up right where I left off. In that time though, I did notice I forgot to write my squared here, because I factored it. Should be n squared plus 4 times n squared plus 4 over over 4 squared. And then just like before, since we have the square on the top and a square on the bottom, we can pull the square out. N squared plus 4 over 4 squared. And then we can take this fraction and split it up into n squared over 4 plus 4 over 4, which turns into 1. That, oh, and we gotta write the square there. That and that are the same. Identities is established, and that proves that this formula will work to create a Pythagorean triple using any even number. So then, just to recap, we used a few methods to come up with a couple formulas, including n minus 1 over 2, n squared minus 1 over 2, and n squared plus 1 over 2, and n squared over 4 minus 1, n squared over 4 plus 1. And then we proved that this will create 3 integers for every odd number, and we proved that this will create 3 integers for every even number. Then I also proved through a few identities using the Pythagorean theorem that using any number n, you can get 3 numbers that are a Pythagorean triple, and if it's an odd number, it will be an integer, which means that no matter if you plug in an odd number here, you will get a right triangle that works with 3 integer numbers. And n can be any number except for n such that n is included in the set of natural numbers. N is greater than 2. There's a right triangle with 3 integers that has a side of every single natural number greater than 2. Now, I'll show you why 2 doesn't work. 2, 1, and 0 don't work. Zero is an even number, so you would plug in 0 squared over 4 plus 1 equals 0. 1's an odd number. You would plug in 1 squared plus 1 over 2 equals 1. 2 is an even number. 2 squared over 4 plus 1 equals 2. The thing about 0, 1, and 2. 0, you get 0. That's like saying a point with a length of 0 and a height of 0 has a hypotenuse of 0. I think it's technically true, but I'd also think you'd be hard-pressed to find anybody who believe you saying that this is a triangle. Same thing with 1. Height of 1, length of 0, this side's 1, this side's 1, this side's 0. Your hypotenuse is technically 1 because if you take a triangle and you pressed it super thin, your hypotenuse and your one side would be the same length. But good luck telling anybody that this is a triangle. And same thing with 2. Only way to make a right triangle is by having 2, 2, and 0. And the reason I don't count these in this proof is because I just think it's cheating, you know? Like, obviously any number, you can pick any number and it's going to be the same. Like, it's just cheating. But the good thing is that these 3 numbers are special, right? 0 over anything is going to be 0. No other number has that property. 1 is the only number that when you square it and add it to 1 is equal to 2. And thus when you divide by 2 is equal to 1. No other number when you square it and then add 1 and then divide by 2 is going to equal itself. 2 is the only number that equals 4 when it's squared. It's the only number that equals 1 when you divide it by 4. When you square it and then divide it by 4. So these 3 are the only numbers that don't work. Alright, thank you for watching. Sorry for kind of rambling on, especially at the end. It's really late now. Like I said, my camera battery died. I ended up editing for a while the first part of this video, and now I'm recording the end. And I'm very tired, and I'm very glad that I'll be going to bed soon. But I really appreciate you watching. I think it's going to be probably a 20-minute video. So if you're still watching at this point, thank you so much. I came up with this in a study hall, like I said, and in one day, and I was really excited about it, and I tapped the shoulder of the guy sitting next to me, and he told me to shut up and to leave him alone. So hopefully somebody out there is as excited about this as I am. I thought it was really cool. I had a lot of fun putting it together. Thanks for watching.